Welcome back to Calculus 2, Section 3.1, Integration by Parts. We're going to go over and establish integration by parts. To do so, let's recall a Calculus 1 product rule. The product rule is a rule for how to differentiate a product of two functions. We let the derivative hit one of the two factor functions, product that with the other factor, and then sum the derivative on the second product function multiplied with the first product function. Well, we know the fundamental theorem of calculus. We can integrate both sides, take the right-hand side, and put an integral on it. We want to integrate with respect to x. On the left-hand side, putting an integral on the derivative of this product. Well, do we know an antiderivative? Of course. This product, fg, if we differentiate it, would produce the integrand d by dx of f product g. All right. Let's do a little bit of manipulation. First, we can use a property of integrals on the right-hand side. This integral with integrand, a sum of functions, by properties of integrals can be written out as a sum of integrals. Good. A little bit of manipulation by moving one of the integrals to the other side. That's going to allow us to solve for the remaining integral. Let's solve for this integral. Moving this to the other side puts a minus on it. And then we have the product function minus an integral equaling the integral of one of the factor functions, product a derivative of the other factor function as integrand. And this is integration by parts. Now, to make it a little bit more palatable, let's introduce some variables, a u and a v. We'll take the u as f and the v as g. All right. Now, in writing out this statement, u equals f of x, that should be reminiscent of u substitution. And in u substitution, after defining the u, you produce the differential. So find the differential du and compute the differential dv. So these are just formal computations. Du becomes f prime dx, dv is g prime dx. Okay, then let's come back to our integration by parts formula. We've introduced a u, we've introduced a v. And then with those definitions, we found differentials. Let's see and plug in for these integrands. F, we know, is u. And then the g prime dx, we can match that. G prime dx, we can match that with dv. And do the same thing on the other integral. Here, let's first identify the g as v, and then what remains, f prime dx, will be the same thing as differential du. So, with these shorthand notations, we can write down integration by parts, or abbreviated IBP, as integral of u dv is equivalent to u product v minus the integral of v du. Okay. So this is the shorthand notation. And the method of integration by parts is to take a given integral, rephrase it in a different form, and hopefully be in a better position. Okay, so here we're presented with some integral. And the way that we're going to employ IBP is to begin by establishing a u. Then, if we've identified a u, then we want to next identify the dv term. After doing this, you then look at the u, and just like u substitution, you produce the differential du by taking the derivative of f. On the other hand, in identifying the dv term, to produce the v term, you want to think about an antiderivative for the g prime term. And g under derivative will produce g prime, so g is an antiderivative for g prime. Okay, let's put this into practice. Let's do an example. So I'm going to use the notation capital I as a placeholder for the given integral. And if we look at the integrand, if we cover up the x, sine x, that's an elementary integral. But sine x product x is not an elementary integral. And this is an example of an integral for which IBP is quite useful. Okay, so let's suppose that we're told how to use IBP. They're telling us to set u equal to the x, and then once we set u equal to the x, everything that remains, assign that to be the dv term. So that's step one, identifying the u, which then everything that remains is the dv term. This is the given integral. Good. The way that you proceed is to now find a corresponding differential du and an antiderivative v. So you know that cosine under derivative produces negative sine, so the antiderivative will be negative cosine. So in the first column you differentiate, and in the second column you integrate. Very good, that's step 2 done. Step 3 is then to recall the formula for IBP. The given integral, having identified u and dv, can be expressed out as u product v minus the integral of v du. If we plug in these pieces, we know that u is x. We know that v is negative cosine x. Write that product down. Negative the integral, well, v has a minus on it, so we can write this down as plus an integral of cosine x dx. And this is very nice because the integral of cosine x dx is an elementary integral. So IBP allows us to begin with something which is not an elementary integral and reduce it down to simplified, simple terms. So sine differentiates to cosine, and we're done. Beautiful. Okay, so here is an assignment for you to practice with. And step 1 of IBP has been done for you. In other words, the u has been identified and the dv. So that's integration by parts. LIATE is an abbreviation for a guideline and how to identify the U term. So integration by parts, the very first thing that you want to do is identify the U term. So LIATE is a guideline on how to do that, where L stands for logarithm. Looking at the given integral, if it's not an elementary integral, and you see that there is a log presented, try letting U equal that log. If there are no logs present, next you can look for an inverse trig. For example, arctangent, or arcsine, or arccosine. If there are no logs or inverse trig, maybe there are algebraic functions, like the example that we did. X sine x. Note that x sine x has no logs, x sine x has no inverse trig, but x sine x does have algebraic x. So then you would let U equal that algebraic function. Barring there be no log, inverse trig, or algebraic functions, maybe there's a trigonometric function, like sine x. And then lastly, your last resort on E is for exponential functions. All right, so this is a guideline. We'll go over examples in which LIATE is useful, and we'll also look at an example where LIATE fails. But most of the time, LIATE is going to be helpful, and it's worth remembering. Okay. All right, so LIATE, if we look at the integrand is the natural log, and that's exactly what the L stands for. So we should give it a try, letting U equal ln of x, which means that dv will be just dx. U is ln, and dv, everything that remains, plug that in for dv. In the first column, we differentiate, and in the second column, we integrate. So step 1, and then step 2. Step 3 is to recall the integral capital I will be uv minus integral of v du. So plugging in u product v gives us x ln of x minus v du, minus v, which is x, and then du, dx over x. And this works out very nicely because x product ln of x is easy. And then the integral is an elementary integral, which we can evaluate. And we're done. So that's IBP, where we used LIATE to guide us in determining the U term. Perfect. So here is a variation on the example that we just did. And use LIATE to guide you in determining the U term. Wonderful. Let's do another example. Okay, so LIATE, this integrand, x squared e to the x, has no logs. Move on, look for any inverse trig. There are none. Algebraic, aha, yes, we do have algebraic. We have algebraic x squared. So step 1 is to identify the U term. And then whatever the U is, look at everything that remains and assign that dv. That's step 1. Step 2, compute the differential du and the antiderivative v. Step 3, recall the formula and plug into the formula. U product v minus minus the integral of v du. Good. Now, look at the resulting integral. And up to this point, the examples have had the integral become an elementary integral. This integral is not an elementary integral. However, comparing it with the original integral, it's very similar. But do you see that something nice has happened? Integration by parts has reduced that power 2 down to a power 1, so that if we do one more iteration of integration by parts, we're going to be in a good situation. So let's term that integral capital J and do scratch work to evaluate capital J. All right, so here's capital J. Doing a second iteration of integration by parts, we can basically mimic what we did on the first iteration. The only difference is that our u term is now algebraic x rather than x squared. Good. So step 1, step 2, nearly identical. Step 3, plugging into the formula x product e to the x is u product v minus v du is the elementary integral of e to the x, which is e to the x plus any constant. Good. Let's go back to where we were. Our scratch work is done. We've evaluated J by a second iteration of integration by parts. Come up with antiderivative x e to the x minus e to the x plus c. If we plug that in, we now have the algebra of distributing the -2. And be careful when you take a minus term times a minus term. And notice that I'm not keeping track of the arbitrary constant. I'm preferring to let the arbitrary constant be arbitrary. There's no real information gained by writing down -2c. Excellent. So this was an example where we needed to iterate through and do multiple applications of IBP. Your turn. Basically mimic the example that we did, but pay close attention to how the negative exponent is going to affect your answer. Beautiful. Here's another example. In this example, look at the exponent to e, it's x cubed. And while it may seem that we want to employ integration by parts, you'll actually find that a more simple technique is useful. Good. All right. So here again, we have a similar looking integral, integrand x cubed e to the x squared. And so far, LIATE has been working well. In the previous assignment that you were just given, integration by parts is not the one-size-fits-all. Neither is LIATE. If we look through and we try to identify a log, there are none. Inverse trig, there are none. Algebraic, we give it a go. We set u equal to x cubed. du is easily computable. But trying to figure out the antiderivative for e to the x squared is a little bit challenging. Okay, so LIATE is useful, but it doesn't always work. How can we make an adjustment here? Well, instead of being excessively greedy on the assignment of u, how about we try, instead of all 3 powers of x, we try only taking 2 in the definition of u, leaving 1 for the dv term. And then by the assignment that you just completed, you know that you can do a u sub in coming up with an antiderivative for x e to the x squared. You get 1/2 e to the x squared. Okay, so the point here is that LIATE is good as an overall guideline, but when it fails, be flexible and just feel things out. Nice. Let's go ahead and work this. So we have u product v minus, we're going to get 1/2 and 2 canceling away, minus the integral of v du. And then x e to the x squared, we've just evaluated its antiderivative, so we can easily plug that in. Beautiful. When you go on and take a course like differential equations, it's going to be helpful to do the algebra of factoring off the exponential term so that our antiderivative can be written out as the exponential product with a polynomial in x plus any constant. Very nice. Let's do another example. Okay, so this integrand, sine of ln of x, wow, that's interesting. How are we going to evaluate this? Well, we're going over integration by parts. Let's give IBP a try. What do we do for the u? Well, there isn't much choice. Let's set u equal to the integrand. What's left over for dv is just dx. V is therefore straightforward. Take a moment to think about the derivative of sine of ln of x. Sine goes to cosine. And the derivative of ln is 1 over input. All right, so IBP, we can formally plug everything in. Let's see what we get. U product v, very good. And then integral of v du, we get a cancellation of x's. And then this integral, which is not elementary, yet it's mimicking the original integral. That is curious. Well, the difference, it's not exactly the original. The difference is that the sine term has morphed into the cosine term. How did it morph? Under an application of IBP. We've seen that IBP can be applied multiple times. There's an idea. Apply IBP once more. So, focusing on this integral, working IBP, produce what we get, and this integral under IBP will become the product of u and v minus v, the integral of v du. The v has an x, the du has an x, and the denominator cancels, and minus minus goes to positive. So we'd have the integral of sine of ln of x dx, which is exactly the original integral. Very nice. Now make sure that you go nice and slow, that you're keeping track of the pluses and minuses, so that when we plug back in, let's go ahead and plug in our scratch work. When we plug back in, our integral turned out to be a sum of terms, but the integral that we evaluate has a minus in front of it, that we get a minus on the original integral, capital I. So you're seeing here the real benefit of using this notation of capital I is it saves you from rewriting, and it also helps you identify that, oh, I have the original appearing both on the left and on the right-hand side, but one is with a plus coefficient and the other has a minus coefficient, which means that we can collect them all together on one side. Looking good. Notice also that when we move the capital I from the right to the right-hand side will have no more integrals. And as such, setting it equal to an integral, you want to make sure that you add in the constant of integration. Fantastic. Last thing to do is to remove that coefficient 2. And we're done. So here is another instance of IBP applied multiple times, but in this case, instead of resulting in an elementary integral, it results in the original integral. And this is a quite frequent occurrence. Right, so here's another example where you can employ IBP multiple times and come up with the original integral. And another type of IBP application is in producing reduction formulas. So IBP, apply it in the left-hand side, n is a positive integer. And if you have x raised to a power n by IBP, you can reduce that power on n. So we've done this example for x equaling 2 earlier. And here you want to apply IBP and just show one iteration, and then this can be done for any value n. Good. So that's called a reduction formula. Next, integration by parts. Up to this point, we've been applying IBP in indefinite integrals. Here is the form for integration by parts for a definite integral, that the product function is evaluated at bounds, and the resulting integral is also a definite integral with the same bounds. So as you might expect. We'll do an example of IBP in a definite integral. Compute capital A, definite integral from 0 to 1, so this is an area, of arctangent of x dx. Okay, go back to LIATE, no logarithms, inverse trig, aha. We do have an inverse trig. So let's employ LIATE, set u equal to arctan, dv will then be dx, take a derivative of u for the differential du. Arctan has derivative 1 over 1 plus input squared, and the antiderivative v is just x. Good. Plug in to the formula. Get u product v needs to be evaluated at bounds minus the definite integral of v du. Very good. Looking at the product, x arctan of x, if we plug in the lower bound 0, that term will go away. Plug in the upper bound, we'll just get arctan of 1. And for the definite integral, we can employ a nice u substitution, letting u equal the denominator. We'll have to keep track of this too. And because this is a definite integral, let's go ahead and change bounds. So lower bound 0 becomes new lower bound 1. Upper bound 1 for x becomes upper bound 2 for u. We have a nice elementary integral that we can evaluate. We know that arctan of 1 is pi over 4. Tangent of pi over 4 produces 1. The definite integral is going to evaluate to ln of 2 minus ln of 1. ln of 1 is 0. Bringing this together, employing the power rule for logs, we come up with our definite area. Very nice. Your turn. Compute this area. And here's a hint. Let u equal rad x. Do that substitution, and you should find a nice integral where you can use IBP. That is section 3.1, integration by parts, and the general guideline, LIATE. Thanks so much for watching. Please like if this video is helpful, and see you on the next one.